In this video, we're going to use what we've learned so far to try to turn a few statements into symbolic logic so that we can tell if they are valid or invalid statements. So what does this mean? Well, a valid argument is an argument where the conclusion is true whenever the premises are true. So if you're given a certain set of premises and you show that they're true, then the argument is valid as long as the conclusion is also true. And this will make a lot more sense after we see a couple examples. So in the following slides, you will see a statement followed by a fact about the statement, followed by an argument. We're going to decide if the argument is valid or invalid. And you'll see what that means in a second. And after we do a couple, feel free to start pausing the video and doing them on your own. So I have the truth table written out for the first one because I was afraid it wouldn't fit. I had to check to make sure it would fit. And let's get going. So we have the question, if I am at the beach, then I swim in the ocean. So let's start right away by saying P is at the beach, if I'm at the beach. And then Q can be I swim in the ocean. Swim in the ocean. If I'm at the beach, then I swim in the ocean. If I swim in the ocean, then I feel refreshed. So now we have an R, PQR. I feel refreshed. Therefore, if I am at the beach, then I feel refreshed. So first, let's turn our three sentences into symbolic logic. If I'm at the beach, then I swim at the ocean is just going to be P implies Q. If I'm at the beach, then I swim in the ocean. If I swim in the ocean, Q implies then I feel refreshed. Q implies R. And lastly, we have therefore, if I am at the beach, then I feel refreshed. So our last piece is going to be if I'm at the beach, then I feel refreshed. And now, how do we put this whole thing into one symbolic logic statement? Well, we have if I'm at the beach, then I swim in the ocean. And if I swim in the ocean, then I feel refreshed. We're assuming both of those are true. So this is an and statement. So we have, I'll put it right here, P implies Q and Q implies R. We have that those are true. And if they're true, if these two things are true, then we have therefore P implies R. Therefore, P implies R. So that is our statement. We want that statement to be true no matter what for us to have a valid argument. And something that's true no matter what is a tautology. So we'll see if we end up with a tautology in the end. So the first thing we have to figure out is P implies Q. Then we're going to have to find Q implies R. Then we'll have to find the and statement between them. P implies Q and Q implies R. And then the last piece we'll need to find is P implies R. And once we have all those pieces, we should be able to fill out our whole table with the and sign. So we'll work left to right here. So remember, whenever we have a conditional statement, it's only false if we have a true, then a false. So in our first piece, we're looking at our PQ columns, our P and Q columns. And we're starting with a true and going to a true, so that's going to be true. Then we have true, true again. But then we have true, false, so that's going to be false. Then we have another true, false, that's going to be false. And anytime a conditional starts with a false, we have a true statement. Now we do the same thing with Q and R. We have true, true, which is true. True, false, which is false. False, true, which is true. False, false, which is true. True, true, which is true. True, false, which is false. False, true, which is true. And false, false, which is true. And feel free to go back and make sure those are right. Feel free to go back and make sure you know why those are right. Now we have the and statement. This isn't very easy to see. P implies Q and Q implies R. So we just look at these two columns that we just built, and we say if they're both true, put a true. If they're not, put a false. So we have two trues there, so we put a true. We have a true, then a false, so that'll be false. We have a false there. We have a false there. We have two trues, so we get a true. We have a false there, and then we have two more trues. Perfect so far. Now, we have P implies R. So we need to look at the P and R column, which are not very easy to look at, so let's just point them out. We have P and R. These are the columns we're looking at here. And it's going in the direction of P then R, so if P is false, we end up with a true. So we have the bottom four are all true. 4 trues. And at the top, we have true, true, which is true, but then we have a true, false, which is going to be false. Then we have a true, false again, which is going to be false. No, we don't. Sorry about that. Let's go back up to the top. We have true, true, then we have true, false, then we have true, true, and lastly we have true, false, which is going to be another false. There we go. Things get a little ugly when you have 8 of them. You have to take your time. So now we have our big end statement, and all we have to do is check if the one on the left implies the one on the right, if we have an implication here. And we have a true, true, which is true. Then we have a false, it starts with a false, so we get true, starts with a false, we get true, starts with a false, we get true, and then these got a little ugly. So far we've done 4 and 4. So now we have a true, true, which is true, a false true, which is true, and 2 true trues, which are both true. So we have a tautology, which means in every case, this situation is true. So we have that this is in fact a valid statement. Valid statement. So moving on, we have some more statements. We have if a train system is not in operation, there are traffic delays. Over the past year, there have been no traffic delays. Therefore, over the past year, the train system has been in operation. So we have the train system is in operation. Train system operating. We also have traffic delays. Q is traffic delays. And you might think maybe over the past year, but over the past year we know is not a statement. So that's kind of a red herring. It's something that we might try to apply here, but it doesn't really fit. We really only have 2 simple statements here, a P and a Q. Which is lucky for you guys because you saw how ugly my handwriting gets when we have a PQR. So, we have if a train system is not in operation. Train system is not in operation. So we have not P, therefore there are traffic delays. So not P implies Q. And over the past year, there have been no traffic delays. So no traffic delays, not Q. Therefore, over the past year, the train system has been in operation. P. So this one's a lot simpler. We just have not P implies Q and not Q. Therefore, P. We have to see if this one's going to be a tautology. So we're assuming the first 2 pieces. So we're assuming if a train system is not in operation, there are traffic delays. And over the past year, there have been no traffic delays. That's where our first 2 pieces come from. Then we have a therefore. Therefore is always an arrow, always an implication. Therefore, over the past year, the train system has been in operation. So now we just have to throw this into a truth table and see what we get. So I have P and Q. At the end of this truth table, I'm going to have not P implies Q and not Q implies P. Notice my use of parentheses. I'm going to be working left to right consistently throughout this problem. You might get a different answer if you do something weird like throw parentheses around here, which would be wrong. So we have to be careful with those. So we have PQ. P is true, true, false, false. Q is true, false, true, false. Now what do we need? I see that we need not P. And not P is just the opposite of P, so it's going to be false, false, true, true. Now we need not P implies Q. So we're going to be doing, and I'll switch colors here. We're going to be doing an arrow, but it's going to be going in this direction. So not P is false, so we get a true, true here. Then we have true implying true, which is true, but then we have true implying false. So this one's going to be false. Now we're going to want to add in not Q, so I need not Q. Not Q. And not Q is just going to be false, true, false, true. And the last piece we need is adding those two together with an and symbol, or not P implies Q and not Q. So now we have those two being added together with the and symbol. So this is and. And we have true and false gives me a false. True and true gives me a true. True and false gives me a false. False and true gives me a false. Remember, an and statement is only true if both simple statements are true. And now for the main event. We'll switch colors yet again. We have this whole piece implying this piece. And we want to see if it's a tautology. And it looks like it might be because we have 3 falses that we're starting with. So we get true, true, true. And then we have true implying true, which is true. So yes, we do. We have a tautology. So this is a valid statement. Valid statement. So now that you've seen one with 2 simple statements and one with 3 simple statements, take a minute and see if you can build the truth table for this, or at least build the symbolic logic statement. The first thing we need to do if we're building a symbolic logic statement is we need our simple statements. So I have P equals, Q equals. Let's see if I need an R. You must eat well. So eat well. Or you must eat well, if you want to write the whole thing. Or you will not be healthy. Remember, we'd never want to have a not in there, so we'll just say you will be healthy. Or just healthy. And then I eat well, therefore I am healthy. There we go. So we have our statements. Our statements are P, eat well, and Q, you will be healthy. So you must eat well is just P. Or is an or symbol. You will not be healthy, not Q. I eat well. I eat well is just P. So we have P or not Q and P. And we want to know if that implies I am healthy. We want to know if that implies Q. So let's see. We have P and Q, where P is, I like to do these in white. It's just a brighter color. P is true, true, false, false. Q is true, false, true, false. Our final statement is going to be P or not Q and P implies Q. So we have the first two with an and statement, and do they imply Q is what we want to know. Are we going to get a tautology again? And you can always read through it and try to guess, try to figure out if you're going to end up with a tautology. But the truth table does not lie, so let's get at it. We have P or not Q, so we're going to need not Q. And not Q is just the opposite of Q, so we get a false, true, false, true. And then we have P or not Q. P or not Q is going to be if it's going to be true if either one of them are true. So this is P or not Q. And you see in the first case, P is true, so we get a true. In the second case, they're both true, so we get a true. In the third case, they're both false, so we get a false. And in the third case, the not Q is true, so we get a true. And lastly, we have, change the color again, P or not Q and P. P or not Q and P. So that's only true if they're both true. But we see they are both true in the first two cases. Both true, both true. True, true. They're both false in the third case, so that's definitely false. And in the fourth case, we have P is false, so we get a false. Now, our last piece is, does this imply Q? So let's use a different color one last time. Let's go to purple. Haven't used that yet. And we want to know if this implies this. So remember, if we start with an F, it's going to be true. So that's a good sign that we're going to be right. True, true there. And then in the first case, we have true implying true. So that's right. But then in the second case, we have true implying false. We get a false. So this statement is actually invalid. And why is this statement invalid? Let's go back to the beginning. This statement, it's the second line which is important to us. The second line is what broke down. So if we look at our pieces, we have P is true, so it's true that you eat well. If it's true that you eat well, what that's saying is it's not always true that you will be healthy. It could be false that you eat healthy, that you will be healthy. And we all know that's true. There are plenty of underlying health conditions that have nothing to do with how you eat. So you might have guessed that this one was true. It seemed pretty straightforward, but it's actually an invalid statement. A human reason it's invalid is because there are plenty of other health conditions that could affect your health. But the direct reason is because the truth table came out without being a tautology. So let's do one more. We have, if it rains or snows, then I read. I am not reading. Therefore, it is neither raining nor snowing. You may have noticed a magical board change. I ran out of space when I was making the video, and I had to pause it, erase everything, and make sure I had enough room to redo this problem. So, let's get at it. I have, if it rains or snows, then I read. So I already have all three of my statements, my P, Q, and my R. P is going to be it rains. Q is going to be it snows. And R is going to be I'm reading. So if it rains or snows, P or R, P or Q, if it rains or snows, then I read, imply R. Then we have an and statement. I am not reading. Not reading is not R. Then we have our therefore. It is neither raining nor snowing. It is not raining and it's not snowing. And if we put all that together, we should have our answer. So let's see. We have P or Q implies R, and not R implies not P and not Q. Not P and not Q. That's ugly, but you can see it up top a lot better. So I realized that I need to do all my nots. I need a not P, a not Q, and a not R. So let's start with that. Not P is going to be the opposite of P. P is 4 trues, then 4 falses. So not P is going to be 4 falses. 2, 3, 4, then 4 trues. Q is 2 T's, 2 F's, back and forth. So not Q is going to start with 2 F's. And then not R is true and false oscillating, so it's going to be false. Not R is going to be false, true, false, true, false, true, false, true. And our first statement that we need, the first piece that we need here is P or Q. Remember, P or Q is true as long as one of the statements is true. And I see here that they're both true, P's true, Q's true, Q's true. The only time they're both false is in the last two. So I get true, 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 false, false. 6 trues, 2 falses. Now I continue and I get P or Q implying R. P or Q implying R. Well, we have P or Q right here, and we have R right here. We just need to see if our implication going left is true. So we have true, true, so it starts with a true. But then we have in the second column, we have a true here and a false here. True implying false gives me a false. Then true, true, but true implying false gives me a false again. True, true again. Another false, true implying false. Then 2 falses are both going to default to true. Now, the part that I'm missing is and not R, so let's write that out. That's the spot that I left open. We have P or Q implies R and not R. So we have what we just wrote down. Let's switch to purple. We have this one and sign this one. Not R and what we just had. So this is only true if both pieces are true. And I see, looking down, the only time both pieces are true is right at the bottom. The 2 bottom pieces are true. So we have everything's going to be false besides that bottom one. So we're going to have 1, 2, 3, 4, 5, 6, 7, but the bottom one is true. And now we need not P and not Q, which is our therefore statement. I'll do that in lighter purple. We'll do that in this color. Not P and not Q is only true when they're both true. Well, that's here, here, and that's it. Only the bottom 2. So starting at the bottom, I have a true here, and then the rest are falses. 1, 2, 3, 4, 5, 6. Now, without further ado, we have our therefore statement. We have the one on the right implying the one on the left. We're looking at these 2 columns, and we're seeing if we have a tautology. Do it in blue. And we see that it's pretty easy once we get to this far, with all of these letters, because everything besides the bottom one is false. In an implication, that means that they're all true in the implication. True, 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 3, 4, 5, 6, 7. And then in the bottom 2, we have true implying true, which is also true. So this monster is a valid statement. So these, you can see, are a lot easier to do when you only have 2 simple statements. When you have a third simple statement, it does get a little ugly. But as long as you keep following through with the work, you get to a correct answer.